Hi guys, the video you're about to watch just needs a little bit of introduction. So this is quite a long video, but I'm not going to divide it into chapters because I believe that if you want to learn electronics repair and you're serious about learning electronics repair, you need to watch this video through. So what we have here is a powered mixer, so it's a 600 watt amplifier, 300 watts per channel, stereo, plus a mixer. And this is mostly discrete components, so it's mostly transistors, not so much ICs. Now this mixer, this job, I will say, gave me a right runaround. I did eventually fix it, but to put it into context, I know some of you guys in the comments below will say, oh, that video was great, that's just the level I'm at, or this has just improved my abilities a bit more than where I was, or I'm sorry I tried to follow it but it's above my current abilities. And that's fine, yeah, because we all have our limit of abilities. And if you guys wanted to know or wondered where my limits were, well, this video is about it. This is about as far down the rabbit hole I can go with a repair job and still successfully repair it. So here I'm going to use a lot of different techniques. There's going to be a few blind alleys, there's going to be some moments of inspiration, and we're going to have an epiphany at the end of it, so I do fix it. Anyway, I hope you'd like to see where my limits are, because you're going to find out if you watch this video, and I'll see you all for a quick chat at the end of it. Okay, here we go guys, enjoy the ride. Hi guys, welcome to another Learn Electronics Repair video. I was going to make something different today. I've done a couple of 3 audio related videos in the last week, and I was going to do a GPU. I have some waiting to repair. And then this morning I had a phone call from one of the local bars with an urgent repair. He said, can you fix this for me today? So this is a powered mixer, 600 watt I'm guessing. Whether they're 600 real watts or 600 pretend watts, I'm not sure. Real ones being RMS watts and pretend ones being peak watts. So I have something I need to fix quickly, and you know, I just could not pass up the opportunity to make yet another video trying to fix something I've never seen before in my life and see whether I can avoid making myself look stupid with this one. So he says the protect light comes on. He says it packed up last night. This belongs to a bar in Puerto Rico, which is not the Puerto Rico in the Caribbean, the island. It is the Puerto Rico which is a resort town in the south of Gran Canaria, the island, which happens to be about 10 kilometres from where I live. I used to live down there. Now I live in the much bigger resort of Playa del Inglés. Bigger resort, more bars, more jobs, yeah? That's the theory. Okay, so let's switch it on. He says the protect light comes on, and let's see what it does. First of all, as is good practice with mixers, I've just taken all the sliders down to 0 before we start. So let's give this some power. It's switched off at the mains at the moment, and yeah, let's put it on the light bulb. Let's put the current limiter so you can just see that up in the corner behind there. Okay, so the light bulb's actually here, and we should just get like a pulse of light. Oh, okay, so it's drawing some power. It doesn't like draw a stupid amount of power, but it's not quite doing what I thought it might do when it's sort of like setting quiescence. But it's not, you know, it sort of dims down, so it's not got a short. So let's switch that off. Let's switch this on and let's see what we've got. Well, like he says, the power light comes on and the protect light comes on. And this is lit up. I think we better open this up and have a look, see what we've got going on inside here. Okay, I've taken the screws out. Let's have a look what we've got. I'd imagine we've probably got class AB amplifiers. And we've in fact got a big piece of metal. So we can't see a lot. I'll disconnect this little cable, which is the power lead by the looks of it. And probably the ribbon as well. And then we'll have to take this out to get to the amplifiers. The reason I think it's class AB, by the way, is because at 300 watts per channel it's not powerful enough really to warrant class G or H, where they have switching voltage rail supplies, and it's too heavy to be a class D amplifier basically. Okay, let me disconnect these wires. I've now disconnected the cable, so I've taken the mixer assembly off, and now we basically have the amplifier section, and I'm pretty sure this is going to be where the problem is. I need to remove a few more screws, or 2 more by the looks of it, and then we can get this metal panel out, and let's finally see what we have under here. Well, having constructed this in such a way that you have to remove a lot of screws, and I still can't get this panel out of here. This is getting to be a little bit annoying. I mean, how difficult can they make this? This won't come off. Oh, maybe. Yeah, so it looks like I have to take the other side off as well, and then the whole thing will slide out backwards. Okay, more screws. I think we might be getting somewhere now. Yeah, it slides out backwards. What a pain in the proverbial, yeah. I mean, is there really any need for this? Get a thing, yeah. Got it. Okay. And we have the amplifier. Let's have a look what we've got. So, straight away, one transformer, linear power supply, a fan on here, a bridge rectifier, so the 2 yellow wires are coming from the transformer, and the red and blue are going to the amplifier, together with the black, which is the center tap. So this is a plus and minus supply to the amplifier. There are some fuses down here which look to be intact from what I can see, and that's basically what we have. Oh, and they've marked some voltages on here on this little test point thing, so we can have a look around. That's what we've got. So we'll see if there's any short circuits first on the power coming in. These are our main power rails then, and we can measure to the black, which is ground. Let's see what we've got. So is there any shorts here? No, the capacitors are charging up, and this one, the capacitors are charging up. So there doesn't appear to be any shorts across the power, which kind of makes sense because the preamplifier's coming on. It looks like this might have a separate winding on here for the yeah, looks like we have effectively 2 power supplies here. So this one is the main power supply, and this one is another, probably a lower voltage power supply for the mixer board. There's 2 fuses, as I said, so we can just check these, and they look okay. So that fuse is okay. That fuse is okay. The main output stage of the amplifier is going to be under here, and there's a fan which seems to be, well, it spins freely. But you can also see down here 2 relays, and I'm pretty sure that these will be switching the power to the main transistors. And this is probably where the problem is. So there may be some issue with the output stage, a short or something, and so the relays are not switching. That's one possibility, which is why the protect mode light is coming on. So I think we have to remove this to get to the output stage, and then let's see if we can see any shorts or problems there. I have the screws out. We can unplug the fan. Now let's see if we can get this out now from behind here, or if we have more obstruction stopping us. to get into this amplifier. And we have obstructions. I can't get this out of here because of the capacitors and because of the speaker connectors, which means I need to remove these to get this out. Yeah, the things, and I have to obviously disconnect the plugs going to them. So let's take these off. Still won't come out. And then we'll have to take the speaker connectors off, the speak-on connectors are they called, which is like 4 more screws per each one. Give me a moment. Actually, it was 2 screws per each one, but it's still a pain in the ass. You've got to remove these to get the heatsink off. And now we can get at it. And finally, we're down to our output transistors. Some dust in here, but I doubt that's going to be causing a problem. We have 4 devices on each one here and 4 on here. Let's check some resistances, or rather I'm in diode mode around here. So we have 4 transistors here marked MJ15004. We have 4 marked MJ15003. So we'll assume these are complementary. One side is NPN and one side is PNP. And these metal cans are the collectors of the transistors. These, I'm pretty sure, all the collectors will be connected together. And the same with these. Yeah. Just get a connection on them. Yeah. Just get a good connection on them. Okay, yes they are. And one side is going to be NPN and one side is going to be PNP. So let's work out which they are without using the datasheet for the part number of the transistor. So if we go to the positive supply coming in, that's the red wire. This will go to the collectors on one side or the other. It doesn't go to this side. It goes to this side. So these collectors are all connected to positive, and then we can say for certain the other ones are all going to be connected to the negative, yeah. So negative collectors, these will be the PNP transistors, and the positive, these will be the NPN transistors. We also have 4 resistors here, 1, 2, 3, 4, which I can see, I'll tell you, not exactly the same value. These are 4.7 ohms and these are 8.2 ohms. And again, we have 4.7 and 8.2, so they're not all the same, which makes me think they are not emitter resistors. They might be in the base, and for some reason the circuit, there might be different value on the NPN and PNP. Are they connected to each other? Let me have a look. No. They don't connect to each other. Do these connect to each other? Yeah, these connect to each other. And these connect to each other in pairs. So I don't think they're emitter resistors. I think they're base resistors. I'll have to take the circuit board out to find out, which I'm probably going to have to do soon anyway. But if they are the resistors on the base, then I should be able to see a diode junction from the base to the base to collector. I can't get to the emitters at the moment. Although actually the emitters will be connected to these. Let's have a look. So if these are base resistors, then we should see a junction between the base and collector, which I have a junction there. And this would be the emitter, but it might be via the relay. No, there's a junction. Oh, no, it isn't. It's charging up. Okay. So it looks like we probably have a base collector junction here with a positive on the base. And it looks like if I go the other way around, we may have like a base collector junction here with a positive on with a negative on the base. And I'm pretty sure that will apply to all of them on the other side from here as well. Yeah. And then this way around. Yeah. So I think they're base resistors. I don't see any shorts. I mean, we can check from the positive rail to these, which I think are on the emitters, but I'd have to take it out, and from the negative rail. I don't see any shorts, but these relays may be part of the reason why that is. I think what I should probably do now is power this up again without the mixer attached, just the amplifier, and see how much current it draws on the light bulb again. You'd expect it with no input to effectively come on bright and then go dim if this is working. Let's have a look. So I have my light bulb again under there where you can see it. I have the meter on volts range. So let's switch this on now and see what it does. And that's drawing some current, and that to me isn't right. I would have thought the amplifier would literally just kind of like light bulb will come on and go practically off. So have a look if we can see some voltages. Let's see if we can measure some voltages while it's doing this. So we'll put this on here. We'll switch this on again. What have we got? So we've got minus 30. Plus 30. So that should be on the transistors as well. Minus 30. Plus 30. So that seems okay. What's on these? Down here we can see these fuses. I expect a lower voltage supply. Well, actually, there doesn't appear to be anything on that fuse. Well, on this fuse, unless I've just lost the connection to ground. Let me just try. No, this supply doesn't seem to have any voltage on it. That's interesting. Switch it off again. So the main power supply appears to be up, and this power supply, the two greens and the brown, I'm getting the brown centre tap, which I'm sure goes to here, seems to be having some sort of problem. Okay, if you look down here, let me just zoom in a bit. Let's check this out to see what we've got. Again, we'll go into the ohms range this time. Let me go on ohms range. Okay, so I'm fairly sure to measure this properly, I'll probably have to take the connections to the transformer off, but from here to here the fuse reads okay, and that I'm guessing goes to here, but it'll also appear to go to here, 1.5 ohms via the winding of the transformer. So again, if I go to the other green wire, that goes to there. If I measure across them, it's going to be 1.5 ohms. 1.1, fair enough. So that's where the power's coming in. Yet I'm not reading anything on these with respect to ground. Do they have a different ground? So there's a brown wire here, which will be the centre tap, and I was assuming that this centre tap goes to the black wire, which is the centre tap here. Yeah, it does. That's what I'd expect. So why have we got no voltage on this supply? That's not right. This meter will switch between AC and DC volts automatically. So let's have a look on the voltage here. This should be AC volts. Yeah. Why does it do that? I'm on auto range. So I won't read any DC volts on here as I was measuring the voltage, but I should read an AC voltage here. No, unless the meter isn't switching to AC for some reason. Let me get my other meter. I think this is a red herring, guys. I think it's just not switching to AC to read the voltage. Let's go to the centre tap. Doesn't matter, that one, all the black one, they're both connected together. Stick it in there. Let's have a look. So we're on volts AC. Yeah. You switched on. What we got? Ah, we got about 12 volts. Yep, 12 volts. 10, 12 volts AC. That then appears to come through a bridge rectifier here. It looks like we have two voltage regulators on the side. Let me see if I can get the part number of them. Okay, so I've sorted that out with this meter, which is my new one. When it's in auto mode, it automatically detects AC or DC voltage, But when it's in voltage mode, it doesn't. You actually have to switch yourself between AC and DC like normal on a multimeter. So that was user error, not test equipment error. So I'm now on DC volts. Let's power this up. This is an LM317 voltage regulator, and this is an LM337 voltage regulator. I'll put the numbers up. So this is a positive supply, and this is a negative supply with reference to the center tap on the transformer, in this case the brown wire, which is connected to the black wire, the other center tap, so we can connect together to those. Doesn't matter which, I'll go with the black one, it's just easy. So the output of the positive voltage regulator is on pin 2, and the negative one, although it's an identical device, for whatever reason of their own making, they put the output on pin 3, and this is common with negative voltage regulators, even fixed ones, 7/8 series, 7/9 series. So let's have a look. So I'm on the output of here, and this should be a negative supply rail if I turn the amplifier on, still with the light bulb in. So this has a -9 volt supply, and that seems quite reasonable. And the other one has a plus 9.2. Let's go again on the negative one. Yeah, minus 9.2. They're basically about the same. So those power rails seem to be there. I've also noticed that there are some voltages marked down here on this connector. So let's zoom in on this and let's see what we have. Well, we have a VCC, which is a power, bias plus and minus left, and also bias plus and minus right. I'm not sure exactly what these are doing in as much as being biased for the output transistors. I don't believe that's what they are doing. So I'm not totally sure what those two signals are doing. We have fan, a minus VCC, so we have a plus and minus supply here. Temperature limit, we have a minus 15 volts and a plus 15 volts. And we have a plus 5 and a plus 24. So we have a few voltages here. So again, we can power it up. I'm still on the light bulb limiter, which may cause some of the voltages to be reading lower than you would expect. But let's have a look. So this says it's plus 5. I'm having a plus 5 supply. This is plus 24. And we have, okay, plus 21. But considering I'm using the light bulb to limit the current, I'm limiting the voltage coming in. We have plus 15. There's actually only reading plus 9 on this. Okay, we have a minus 15, which is reading minus 9. That's the supply we were just looking at. We have a minus VCC, which is, yes, the 28, and the plus VCC will be the 28. So it's looking like that plus and minus 15 are only plus and minus 9. But that might actually be just because I'm using the light bulb limiter. So now I'm going to have to switch that out of circuit to get any sort of sensible reading from this. It's not drawing a stupid amount of power. So we now powered up directly from the mains. Let's have a look now what we got. So plus 5 still there. Plus 24 is now plus 25. What's on the plus and minus 15? Well, plus 16, minus 16, so that's probably right now. The VCC is now plus 64, it's proper voltage, and minus VCC is 64, so that's what's now on our transistors. Okay, so the old amplifier is powered up. Why are we having this protect signal? To answer that question, let's use some high technology, a pen and a piece of paper. We know we have a plus, I think it was 64 volt supply, something like that, and we have a minus, I think it was a 64 volt supply. And then we have 2 NPN and 2 PNP transistors in each amplifier. So what we actually have is we have a transistor like so, and we have another one. So these are in parallel basically with each other. So we have another one, like so. This is the base, this is the base, and then we have the PNP transistors. So we can draw one here, this is the base, and we have another one here, again the base. So we have 4 transistors like this on each channel. So this is one channel of the amplifier, and these points will connect together. I'm pretty sure, but we can test this. We could have a bridge amplifier here, but this is our amplifier basically. It's either going to be a speaker in here because it's acting as a bridge, or these 2 points here will connect to chassis via the speaker. It's going to be something like that, probably this one. So that's what we've got. And we know somewhere in here, going to somewhere, we have base resistors, and it looks like 2 of the bases are connecting to one resistor one way or another, and the other 2 are connecting to the other one. But again, I didn't completely check this out because I can't get the thing, well I can get the thing, but I haven't opened it up yet to see where the emitters are. We can see anyway from here, from these resistors, a diode junction there to the collector, and we can see we have NPN, which are the MJ15003, and we can see PNP, which are the MJ15004. So that's what we've got, and we've got a protection error coming on for some reason. We know the voltages are okay. We know we've got the voltages okay, that's for sure. We also have another smaller power rail with a centre tap again, and this has the LM317, and it has the LM337, and these are giving us plus 15 volts and minus 15 volts. Yeah, and the grounds will be connected together to chassis, which is basically the centre tap of the winding. We can put the winding here, secondary, and we can put some diodes in here just to make the circuit work. Okay, always have to remember which way around to draw the diodes. We have something like that, and we know these voltages are correct, and we know these voltages seem to be correct, and we know at the moment we have no drive to the amplifier because we've disconnected the preamp, so there's no audio signal coming in. We also know the light bulb comes on at about half brightness, and when the light bulb's in circuit, this was about 30 volts thereabouts. I can't remember exactly because it was 10 minutes ago. Yeah, but we know with the light bulb limiter in circuit that the voltage here is about half of what it is without it. So we can kind of, as a rule of thumb here, figure out my light bulb's a 60-watt light bulb. So when the light bulb's in circuit and it's about half brightness, this amplifier is probably drawing like 20 to 30 watts to light the light bulb up. Just guess, yeah. I mean, I could measure it with a AC ammeter, I suppose. I'll have to buy one of those ones that clamp on the wire, actually. That'd be handy. But we have something like that. We know, as far as we can tell, there's no shorts here and here. And we think there's no shorts through to the emitters, but we don't know because we haven't got to them yet. So why is the amplifier drawing power in its quiescent state, and where's the power going? Yeah, because that's a fair amount of power. Well, it could be that there's some short circuit to the emitter, and we'll have to take the circuit board out to find out. I can't see any short reading to the speaker terminals. But having said that, in here somewhere on both channels is a relay, and it could be that the relay contacts are effectively here connecting to the speaker. Yeah, so the relay is powered and switches on or off. And to switch it off, you don't need a protection area, you need the top circuit board to switch it off. That, well, to switch the relay on, sorry, so you get power to your speaker. It seems something like that. What we could try, there's another possibility that we don't have a short here, but due to some problem in the drive, that one pair or other of these transistors is basically being switched on. Because this is our drive, yeah? In the quiescent state, both these transistors should be only just switched on. There's a bias network that sets it so that they're just slightly switched on, and they pass in like milliamps, yeah, I don't know, 20 milliamps, 10 milliamps, 50 milliamps. They pass in a low current in the quiescent state, and the same with these, yeah. If there's some problem with this bias, so that one side is switched on and the other side is switched off, basically when it's quiescent, you'll get a situation where the voltage here at the middle is not basically zero. It should be basically zero, because in the quiescent state your speaker cone should be just in the center. It shouldn't be one way or the other, it should be center. So there should be a very low current flowing through here. Can you see that? So the voltage here should be practically the same as the voltage here, and if it isn't, that would probably give the protection area. So we now need to test for two things. One is one side being effectively switched on when it shouldn't be, and the other one is there's some problem with the collector emitters. There's a short somewhere that we just haven't seen because of the relays and the fact we can't get to the emitters yet. It might be possible to measure the voltage on the base resistors to see if one side of the amplifier, the positive or negative half, has got drive all the time and it shouldn't have. And I don't know what the voltage should be, but what I do know is I have two of these channels and they're identical, and there's a very good chance, well, depending on my luck, for most people there's a very good chance that only one channel has got a fault on it. So the first thing we'll do is let's look at the voltage on the base resistors. We can see 4 of them, if they are base resistors, and let's see if they're all the same compared with the other channel. If they are, or even if they aren't, we're going to have to get the circuit board out then and investigate what the problem is. Okay, back to the unit. Here's the amplifier again. I've just connected these back on. They're loose, but the wires at some time look like they were very close to touching each other. I don't want to short anything there, so I'll just connect them back onto these just so they can't actually touch each other. Not easily, unless the thing actually falls out and touches the chassis, but that would take a bit of doing, yeah. So we can again plug this in, and let's have a look now at the voltage on these 4 resistors. And I say I don't know what this should be, but I do know that these two should be, you know, like these probably a pair, and these are probably a pair because they're different values to each other. Let's see if there's any difference. If there's a difference, we know we've got some fault on one of the channels to do with the biasing. I'll just switch the meter on. And there we go. Somebody was asking when I reviewed this, how long do the batteries work? I don't know. I've had it for a few weeks now. I'm using it regularly, but I still don't know the answer to that. We'll find out eventually. Okay, stick it here where we can see everything. Get the reflection off it. There, right, we can see it. Good, now we can begin. So we're going to measure to the ground point. I'm going to use the brown one this time because it's easy. No, I'll get the black one. It's easy. It's there, yeah. You can't see it, but it's there, yeah. Now let's power it up again and let's see what's going on these 4 resistors. So we want volts mode DC, okay, and we'll switch it back on again, and let's see what we have now. So this resistor has practically nothing on it. That's fair enough. Just make sure the meter's working. Yeah, that's practically nothing on this. What's on this one? Well, wherever they are in the circuit, they have practically no voltage on them. What about these two? Just get it where you can see the meter. That has practically nothing on it. And they all have practically nothing on them. So wherever they are in the circuit, there's no difference between the two channels. So that's told us absolutely nothing whatsoever. So I think now we have to get a circuit board out and have a look, see if we can see anything else. Okay, I've got the circuit board out. Got quite a bit of dust off it, but I don't honestly think that has anything to do with the problem. So have a look now under here. So we can see where the transistors are. We can now see the base collector emitter. Reposition the glasses. These resistors that I thought were base resistors, well, one's over here and the other one's over here, and they not, well, they sort of like connect somewhere where these relays are. These relays look like they take the power. This is the main power coming in. Yeah, this is where we were, the red and blue wires. So that clearly goes to the relays, and then the other side of the relay switches power, I'm guessing, to the transistors. It looks like it goes, let's have a look if we can figure out where it goes. Yeah, let's get the meter on ohms range, one moment. So power comes in here on the relay, and these are going to be some thick yeah, okay, I can see these here. These are effectively like your connection to your speaker, which is these big ones here. One end goes to the power, then the other end looks like it goes, these are the relay contacts, so this goes to the relay, and it goes down to this big inductor coil here, and the other end of the inductor coil, oh, it goes through, oh yeah, more resistors, yeah, these are your emitter resistors. I can see them now, 1, 2, 3, 4, that's where that goes to. Then the other end of the resistor goes to the emitter. Okay, now we can see it. So we do have emitter resistors. I thought we might have. So now we've found the emitter resistors, we better check them. The value on them, a bit odd to see it's kind of behind the relay, but I can tell you that they're 5 watt 0.22 ohms, yeah, which is quite common for these sort of resistors, emitter resistors. So one of them we have just found, and we know is here. So this is effectively the emitter of one of the transistors, and it goes to here. And this here looks like the emitter of the other one, which goes to here. You know, that's how it seems to be. So the resistor's actually there, and it reads, yeah, 0.2 of an ohm, just a little bit higher. Oh, it's a bit higher actually. I thought it would not read. Depends how well my meter is zeroed. What's this one reading? 0.06. So it basically reads the same. And then on the other side we have one here, 0.06, and we have another one here. That one reads 0.06, the same as the other ones. So this looks like it's the base of these two transistors, both connected together, connecting to a transistor here. This must be driving it. And I'm pretty sure we'll find the same thing on this side. Yeah, two bases going to here. And the two emitters seem to connect together via a resistor. And then I'm guessing this then goes to the relay somewhere, to some switching contacts. Yeah, it looks like it goes to there. Same off the other one as well. If I just get to the other emitter. Yeah. So those go to that switching contact, and I think we can come onto this side and say that the two emitters, which this is one of them, yeah, goes to this contact of the relay. So the relay is effectively switching the speakers, because the other side of the relay is the wires which go out to the speakers. These, yeah. So one of these is connecting to the other contacts on the relay here, and then the black one, I'm pretty sure we'll just find out. Is this going to ground? Yeah. So the diagram I drew, where it wasn't in bridge mode, that's actually what we have here. That's what we've got. So that all reads okay. How about the transistors? How do they read? So let's get on to diode mode. One moment. Diode mode. Get the wire out of the way. Okay. So, because they're effectively in parallel, it's going to be a bit hard to read. I certainly probably wouldn't find an open circuit one. That is 0.156. I'm guessing it's going to be the same. Yeah. 0.156. Which is not exactly what I'd expect for a base diode junction, base emitter junction, but it may be just components around, and they're reading both ways as well. So look at this one. Yeah, that's reading the same. And there's 4 on each side, isn't there? There's another one here, and there's another one. 1, 2, 3, 4. Yeah, that's 4 of them. So they're all basically reading the same. What's happening on the NPN side of it? So they measure about the same. And do these measure about the same? I'm guessing they probably do. Yeah, so they all measure about the same. But I can't exactly say if the transistors are good because of the way they are reading in circuit with these resistors around them. The only way to be absolutely sure would be to take them out and test them. How about base to collector? So we know base emitter is sort of reading, but we can't say it's good or bad. These metal studs here, I think, are actually bolted to the heat sink, and the heat sink, if I go to the actual collector of one of the transistors, is it connected to the stud? Yeah, just check out another one. Yeah, they are. So the collectors are connected to the studs, and the same on the other side. Yeah. So we know that these studs are the collectors. So these are the NPN transistors. So we should see a diode junction here, which we do. Do we see anything the other way? Yeah. No, we don't. Just capacitor charging, as you would kind of expect. So we see a diode junction here. We can see one here. And I'm assuming on the PNPs it's the opposite way around. Red to here. Yeah, diode junction, diode junction. So we know the diode junctions look okay. So I don't think we've got any shorts here. Or defective transistors. I mean, I'd have to take these out to be absolutely certain. How about the driver then? So the 2 bases here come back to a little, it's hard to show. It's there, it's a transistor, yeah. They go to there, and the same on the other side. But hard to show you what was a transistor under here. So we can follow the track. So these are the 2 bases, and they go to here. And then this would be, I would imagine, emitter collector base. This I'm thinking is the input. Where does this go down to? Let's have a look. Well, it looks like it goes to a resistor or something. Here. Hard to say without taking it off. Oh, that looks like a resistor between there and there, probably. And I know there's tracks on the other side of the board as well. So I'm thinking that the base of this probably comes from these pairs of transistors down here. Via well, there's quite a low resistance there. Yeah, I mean, there's a track which goes from this one. That goes to here. There's a one I can see that actually goes up here somewhere. Well, this one goes to here. Then it goes, I think, through a resistor to here. Oh, and that looks like it goes to the base of this one. Yeah. So I'm guessing the 2 bases are somehow being connected down here. One of them I can pretty much see. So it goes from here. Let's put it on ohms range. See if I can see it on ohms range a bit better. So one of the bases of the drivers, that's driving this base, that goes through, looks like a resistor here, which reads about 100 ohms, and then the other end of that goes down to this transistor here. Yeah, and I'm guessing that the other base, the driver to the base here, is this one. It's probably going through another 100 ohm resistor somewhere down to here. 123. That's hundreds of kilo ohms. Yeah, centre of that one, 123. It's a similar reading, isn't it? So that looks like this is driving the two base drivers that are driving the main transistors. Yeah, so that looks like where that's coming from. Let's see if we can compare this channel with this channel again to make some sense out of this. So that's the base drive. This will be the base of this transistor, I'm sure. And we know that that comes down to here via 100 ohm resistor, 101. And we should be able to find the same thing on this side, which is here. It's kind of mounted the other way up. This is the base drive. So from here to one of the centre pins, you expect to find 100 ohms. Yeah, that's 101. That's the same. So that is driving that. And then we have the top one. So again, that's driving the base of the output. So this end is the base of this transistor. And you'd think that comes down here. Well, 123 is what we had. And we could do the same with this one. So from the top of here, you would expect that comes down to the middle of the other one. 123. So they look the same. Both these channels, as far back as the centre pins of these, look the same. And it's fairly obvious that these are driving these. So now I'm going to put this back together and measure the voltage on the centre pin of each of these to see if I can see some imbalance between the positive and negative half of each amplifier. So really, this is all still a bit inconclusive. We haven't found any reason yet why it's not working, but we do know now that these relays have to switch on to connect the speakers, and we don't hear the relays clicking. So that isn't happening. So we'll just power it up again. I'll just put on the light bulb to make sure I haven't caused any problems while I was doing that. No, it's fine. I'll switch it on. So again, yeah, the power supply is there. So what's on the middle pin of these transistors? I don't know, but they should be the same on both channels. So this one minus 11.6. On this one 1.467. okay, so on these two, move the meter so I can easily get to it. Okay, so these two, (1.47) minus 11.5. So I'm absolutely confident that this amplifier output stage is balanced, if you see what I mean, that it's not from here being driven one way or the other, unless there's a problem somewhere the other side of these driver transistors. I guess the way to figure that out is we're going to have to power it up with the board out so we can actually measure the voltage on the base, unless I can find somewhere on this side of the circuit board that I can easily do that. Well, it looks like the only way to do this is with the amplifier upside down, basically. So I've propped it up on something, I've got it on the bench, I've got the meter there, I have the light bulb currently, we just switched in again just to make sure I haven't shorted anything. No, it's not going to go bang. So let's switch it on again and then let's have a look to see what we've got. So negative is going to be basically here. And then we have the base rails, we can see them. So there's one here, which is reading 0.61. So that's effectively switched on or just about. This one, minus 0.57. Yeah, this one, minus 0.578. This one, 0.61. So that sort of looks okay. I can probably get a better idea if I measure base emitter. It's probably the same. 606. Yeah. These ones 603, 602. I'll measure them both here. 605, 604, and then we can go on to the negative side. So these will read minus basically. So we have one here, 0.564, 0.563, and we have this one here, 0.568, 0.567. So they're basically all reading similar. I mean, one side, the negative half, reads lower voltage than the positive side, but probably the switch on voltage is slightly different for the NPN and PNP transistors. But the fact that both channels are reading the same effectively, and I think probably only one faulty channel if there is a faulty channel, I don't think that's the problem. So I'm thinking now maybe the fault isn't on this amplifier board at all, or at least it's not on the output stage. It seems more likely that either A, this is sending an error signal to the other board, so it thinks for some reason we have a protect error when in fact we don't, or that there's a problem on the other board, the mixer board. Let's just switch this back on again. We'll just check one other thing. So we're back on. So we'll now go to ground and we'll look at the emitters. So this is ground effectively. These emitters should be basically 0, so 0.012 of a volt. So that transistor is basically off. That one is basically off. Yeah, they're both basically off. In fact, the voltage is going down slightly for some reason. Maybe it kind of auto corrects. You just switch it on for a little bit. 0.006, 0.004. This is what you'd expect. You'd expect the emitters to be pretty much 0, and they are. Now I'm convinced that there's nothing wrong with this amplifier, unless it's erroneously sending a signal, a protect signal, to the other board. So I'll put this back in, and then we're going to have to see if we can figure out why we're going to protect. Well, I've just unplugged it, ready to put this back in. I've found that something here is getting warm. Something here is warm. And behind here, we have like a whole row of like transistors. So maybe this is actually where the problem is with this. Let's put it back in and let's see if we can figure out what's actually getting warm. That might give us a good idea as to why it's doing what it's doing. Down behind these heat sinks, I'm sure you can see them, there's a whole row of transistors. Well, I say transistors, I think they're transistors, I mean they might not be. But can you see them down here? And we actually I've counted, there's 16 of them. So there's like 8 per side, I'm not really sure, and there's like a whole row of resistors that go with them as well. And something down there was warm after I'd unplugged it. So maybe this is related to the problem. I don't honestly know what they're doing because I'm not familiar with this. I can't say I've ever noticed that on other amplifiers I've worked on. But they're there, you can see them in the back, they're there. So let's try this with a little toy. This was sent to me by a subscriber, actually sent me this. And it's a thermal imaging camera. I've never used one before. I had a little play with it when he first sent it to me about 2 weeks ago or so, maybe a bit less than that. And I was going to use this, I was going to review this, and in fact I will review this. But this seems like a perfect opportunity to actually try it. So he's saying the battery's low, but hopefully it'll last long enough for us. Well, let's see if I get us into this shot so we can actually see. Yeah, I mean you can see the transistors now. Maybe if I tilt this up a little bit, yeah, we can see the back of it. We can see the holes where the actual we can see my finger, which is bright. Yeah, this is where the cables go through. So let's see if I can get us into a position where you can see it, I can see it, and we can actually look at down here with it and see what we can see is actually getting hot. Okay, so it's powered up. Now let's have a look to see what we can see. And straight away I can see behind here something is glowing very brightly. Can you see it there? In the middle, 1, 2, 3, 4. And the main output transistors, let's have a look. I thought maybe they were glowing, but they're not. I think that's just changing as I'm moving the position, but something behind here definitely is getting very warm. I'm just seeing it's there where my finger is now, so I can basically see where it is. So let's have a look to see what that actually is, and I think that's probably our problem. Okay, I have it out. Something here is hot. I think it's this capacitor. Yeah, it's all the transistor next to it. Something here is hot. Let's have a look to see what these actually are. But I think we've actually found the problem, and I think it's probably this one. I've now balanced the amplifier board so we can see these transistors as 6 there, 6 there, and 4 there. So there's actually, as I said, 16 of them. I'm now going to take this thermal camera again, and let's see if we can see which one is getting hot or getting the hottest. Yeah, so we'll hold this above this. It's now ready to switch on, so I'm on mains. So I'm going to power the thing up. Well, let's have a look what we have. So let's have a way you can see it without reflection. This is going to be a bit awkward, guys, but I'm sure. Right, okay. Something there is glowing like a light, yeah? Right, so we can see what the problem is. Yeah. Now let's just figure out which one it is. So let's take a pencil and move it across. There. It's the one nearest the capacitor. And it's glowing like a light bulb in here. Sorry about the reflection off my overhead lighting, but you can see it there, yeah. So I think that is the problem with our amplifier. This is the one that was getting the hottest. So let's have a look to see if we can see a short or something. So it's actually this one. What is it? Or what's it supposed to be? Well, what's that, emitter and shot, and we can find out. So we'll just go into diode mode. Okay, we're in diode mode. So it's this one. Well, it doesn't read short. Well, it actually reads like a transistor. It actually reads like a transistor, so maybe there's something else that's causing this to get hot. Let's take it out of the board and let's have a look first, just to be sure. But I honestly expected to find a short circuit here, and I don't have a short circuit. And we can see that, I'm pretty sure this is the base, goes down to this resistor, which looks like it comes back up here to the next one. That, interestingly, this one, these two pins are connected together. Yeah, those two pins are actually connected together. But only that one, because the next one doesn't have anything connected together, but only that one does. But it's obviously deliberately that one's connected together. That's like having the base connected to the emitter. Is it, they're just using this as a diode. Let's have a look. We'll take this one out first and see what it actually is. I've got the thing out of the board. I had a quick look. It's actually marked BF393, whatever that is. Let's see what the component analyzer thinks it is. It looks like a transistor and circuit, I'll be honest with you. It looks like a good transistor and circuit as well. So let's see. Get all these little wires onto it. One moment. Okay. What's it think it is? Well, it sells, it's a transistor, and it's good, which is how it looked in circuit, and yet it's glowing really bright. I mean, that doesn't mean it's like as hot as a light bulb. I mean, obviously, it's just a few degrees hot. Well, no, actually, it's hot enough to warm. You can feel it's warm. So why is that getting hot? Because the transistor itself is okay. So there's got to be something else in the circuit around here that's making this get hot. I had a look at this a little bit closer, and they're not all the same. So the first two are these BF393, and this one tests okay out of circuit. And then the other 4 are a mixture of MPSA 43 and MPSA 93, which are NPN and PNP, and they're high voltage transistors. And then the same here, we have 2 of the BFs and the rest of these MSAs again, and these are the MSA ones. So it's maybe that this transistor effectively is powering something down here that is short, and that's why it's getting hot. But the circuit's looking now, it's going to be getting more complicated to try and work this out. So I thought I'd take a chance and see whether I could find a schematic for this, which you'll probably say I should have done in the first place, because actually I did find a schematic for it. So let's put this back in, because this is obviously not faulty even though it's getting hot. And then let's look at the schematic and see if we can figure out exactly why Q148 would be getting hot. I found a schematic for this Dynacord Powermate 600, but it doesn't match my board. Looking at like the part numbers here, Q140, Q141 and so on, they don't exist on the schematic. It doesn't match this for some reason. So I then thought it was the weekend, I'll ask on Badcaps forum in the audio repair section. So I posted some pictures and showed them this is getting hot and a description of everything that we've done, but unfortunately I don't have any replies at all, which is a bit unusual. So it's Monday morning now, I've had a weekend to think about it. It looks, if you have a look at the circuitry, I'm sure you'll agree with me, basically symmetrical. So we have, if we start from the middle, we have 2 transistors and the capacitor going each way. Then we have the 6 transistors, and then we have 1 here and 2 pairs here and here, and the same on this side. Yeah, you can see it's same, the capacitor, the 6, and then the 2 pairs. And this one, capacitor here, one of these here and here, looks like another capacitor. So it looks like a very symmetrical sort of circuit, and I don't really know what this is doing. I mean, even this looks symmetrical, but I suspect this is probably something to do with monitoring the output waveform, whether it's clipping maybe, or this is what the protector's for. These 4 transistors are these MPSA 42 and 92, which are complementary pairs, NPN, PNP, and the high voltage transistors. It says 200 volts. So I'm assuming the only thing with any high voltage here is you know, the waveform coming out of it. These are the BF393s, and this is the one that gets hot. But the transistor's okay. We've checked it. We know that's okay. And then the same on this side. We have the 2 with BF393s and the other complementary pairs. Then it looks like we have some resistor type things here, or thermistors. I'm not quite sure what they are. Voltage dependent resistors. They're marked as R, but there's something unusual about them, like they're not normal resistors by the looks of it. So I have 2 ways I might go about this. Well, 3, but the first one didn't work because nobody knows, it would seem, and the schematic doesn't match. Well, if we have 2 kind of identical circuits, then I could either measure the voltages on this one and compare them with the same on the other side and see what's different. I'm assuming because this one's hot and this one isn't, there must be some difference, and maybe then be able to trace back what's going on. But before I do that, I think I'll check all the transistors in each direction to see if I can see any differences on the 2 sides. And if I can see any difference, that might be giving me an indication, especially if there's low resistances or shorts on this side. That seems to be worth a try. So let's have a look and see if we can see any difference between them. It's upside down now, so this is the bad side, the one with the problem. This is the transistor I removed and tested. Let's have a look. So kind of working from this end of it, we have 2 transistors here and 2 here. If I just put the red in the middle, that's the base. So we seem to have a junction there, and really an open there. What's the other? Yeah, junction. That was like a NPN. Yeah, PNP. And then I can go to the other side basically and do the same thing by finding the same two transistors on the board, which are over here, and just compare them to see if they look the same. Yeah, so you see what I'm doing. Now, this is going to take me 5 or 10 minutes just to go through them all, so I'll go off video, save you guys waiting. I'll just check through them all and see if I see any difference obvious between the two sides, and that might give us a clue as to why this transistor is getting hot. I've worked around all the transistors coming inwards, just checking each side and working in, and they all basically look the same. I'm getting to the point where I have the one which was basically getting hot, and the transistor reads okay, but the one next to it basically reads short base to collector, and I thought, oh, I found it. But if you look at the PCB, I think you can probably see that the base and collector are actually connected to each other. And if you look on the other side, it's slightly different. So this transistor appears to be the equivalent of that one, and the one with the base collector is actually here. And again, on this transistor, if we look at it, base is connecting to the collector as a short. That's quite an unusual configuration for a transistor, so I had to look it up. And basically, when you get two transistors and one in a particular circuit, and one has the base collector shorted, that circuit, the two together, form a constant current source. You can go and look it up if you like. I'll put a link in the description to this video. But I'm not particularly bothered about the inner workings of it, just effectively why. And I know why now, it's a constant current source. So that brings me to these four in the middle. Now, if we start from this end, this is the outer end. You can see on the meter 0.666, 0.649, that's effectively the base in the middle, yeah? That's that one. But this one here on the other end, though, reads 0.139. That reads pretty much the same. But it reads different, this here. 0.139, yeah. If we go to the other two, so I think it's a PNP, NPN. Let's see what we have on this one. You have a junction there, a junction there, and it reads like a junction that way. And this is the equivalent on the other side, if it's symmetrical to this point. Yeah. So the difference I can find basically is on this transistor here. We see a junction, and on this one we see a very low resistance in comparison, and this is the side that has the problem. This is the one that's getting hot. So I'm going to take this one out and have a look to see if that in fact is a faulty transistor. Here's the transistor ID soldered. It's MPSA92, which is one of these high voltage transistors, 200 volt. I can't remember if the 92 is the NPN or the PNP. Let's have a look on our test meter on diode. Let's see what we've got. So I know the base is in the middle. Okay. Is that reading? That reads okay. Oh, but I've got a reading directly across it. Collector emitter, that's not good. Let's put the one here. And I get this low reading as well from base to emitter or collector, whichever way it came out. One moment. Base to collector reads low, that's not looking good at all. Let's put it on the little peak analyzer. Let's see what that stinks of it. So I'll just try and get into the shot for you. Okay, so we have it. What's this tell us? Unknown faulty components. Okay, so that is a bad transistor. That's the one that was basically sort of next to the faulty one. So this is the, well, faulty one. This one was getting hot. This one is faulty. I'm inclined to take the other one out as well and just check that one, even though it looked okay in circuit, just to make sure, because I think it's connected kind of to this one by the looks of it. I'll take this one out as well, just really as a double check. This is the one that was next to the faulty one. So let's have a look at this. It's the same device, MPSA92. Let's just a bit awkward, but let's see if we can just test on the multimeter, then we'll try the analyzer again. So that reads good. Yeah, that reads like a good junction both ways, and open between the collector emitter like you'd expect it to be. So let's put this on the peak analyzer and see what it tells us. Okay, we have it attached, we have it upside down, and the lead fell off. Okay, let's go again. So we have it on there with all the leads the right way up. That might help. That was my other meter just switching off. Yeah, PNP silicon transistor. So this is a good one. Gain 180 test current. Okay, so that's a good one. So let's have a look at these transistors now. I have to see if I have anything here that's a suitable replacement for one of these. I'm on alltransistor.com, or I will be in a moment. This is a very good place to find data sheets and equivalent transistors. So we have an MPSA92. That is our transistor. Let's have a look. Search. Well, yeah, it's found it there. MPSA92. Get rid of the advert. That's the only annoying thing with this thing is adverts. And it's silicon transistor, 300 volts. So it's a high voltage transistor. I thought it was 200 volts. And we have a data sheet here for it, so we can have a quick look. Okay, MPSA92, 300 volt transistor. Yeah, the 93 is 200 volts. Okay, so that's what we have. Can I find something suitable to use? Let's go back. Equivalent substitute. What have we got? Well, it's given me some equivalents here. So the first thing I really need to have a look is go through my little stash of bits and see if I can find anything that might work in replacement of this transistor. Unfortunately, I don't have anything like this at all. There are 300 volt, half amp, 500 milliamp PNP transistor, and I have some PNP transistors not on the list of alternatives it gave me, but that are 300 volts, but they're only 0.1 of an amp, not 0.5 of an amp. I have some NPN ones that are suitable, but I need PNP, so I just don't have, unfortunately, transistors I can put in here, which means I'm going to have to order some, which is a bit of a pain in the butt because the guy would like us back quite quickly. I'll see if I can find some maybe on eBay or something from China. They're going to take quite some time, but at the same time I need to order a pack, you know, each of these, and also the MPSA 42, which is the equivalent, but NPN is the complementary rather than not the equivalent, because I need to keep these in stock. So about a week or so has gone past since I made most of this video, and I now have from the Capital, that's Powermate, the transistor. I have a friend who goes to the Capital every Friday basically, and he gets to it for me. So here we have our replacement, or a compatible BF491. That's what they've given me. Let's have a look to see if this actually is compatible first before we fit it. Here is the transistor, the original one, MPSA92, PNP, 625 milliwatt, 300 volts, 5 volt emitter base, half amp, 50 megahertz. So that's the original one, and the one they've given me is actually not on the direct compatibles list, which this site gives me. It's a BF491. What they've given me is this BF491, same wattage but 200 volts, half an amp, and a similar gain. So it's a very similar transistor, but it's 200 volts rather than 300 volts. However, I know this amplifier, the voltage rails are about plus and minus 60. So I don't actually see how this transistor could ever be subjected to more than 120 volts. And I'm fairly confident this is actually going to work. At the end of the day, it can't make it any worse, and we can connect it with a light bulb and circuit. So let's put this transistor in. I'll just check the pin out first to make sure that is the same, and then let's see if it actually does work or not. I've put it back together enough to test it. I'm connecting through the light bulb again, so we can have a quick look at that, which is over there. Let's see if the protect filter's gone. So we'll just put it with the light bulb first, which was kind of coming on to a certain brightness before and getting dim, so that's kind of okay. Let's put it directly onto mains and see what happens. And we still have a protect fault, so we have to go further with this one, unless that transistor isn't suitable. It's a bit hard to get this positioned on the desk where I can zoom down, but basically this is the one I actually replaced here, the PNP transistor. So let's have a look to see what we're reading on it. Well, we have a diode junction there, that's base emitter and base collector. So the transistor hasn't failed again. And the one that's glowing, no, I can't seem to get a reading on this one. Let's have a look. Okay, that's base collector and that's base emitter, so that's actually okay as well. So they still read okay. I think the next thing I need to do here probably is to measure some voltages around these two transistors, and you can see probably on the other side we have effectively the equivalent, which is these two. So I'm going to measure the voltages on the one I changed and the one that's hot, and the same on the other side to see if I can see any difference in voltage. I'll try and zoom this down a little bit so you can see where I'm probing. Yeah, it's a bit awkward to get us in a position where you can see what I'm doing and I can actually see what I'm doing as well at the same time. So we'll have to do it like this. We'll go into volts. I'll clip the ground on somewhere. That makes it easier basically while I'm actually working. I'll just have 1 and 3 then. So I've got it ready to switch on. It's powered up. I'll just switch the light bulb out so it's on power. Now let's have a look. So this is the one I changed. This is the emitter, and that's got 65 volts on it. So let's make a note of that. That's 65.5. I'll show you the notes in a bit. So that's the emitter. Then we have the base, 64.9. Okay, so that's like this transistor switched on by the looks of it. Let's go on the other leg as well. Collector, 65. And these are positive voltages. That's that one. Let's have a look at the other one. So this is the one that was getting warm. Emitter, minus 14.1. What's on the base? Minus 13.7. And on the collector, 63.6. So that's that one. Now let's look on the other side, effectively, like the same transistor on the other channel. So that's this one, 65.8. Base, 65.8. Oh, okay. They're both 65.8. I can see a difference here. Collector, minus 65.2. Okay, it's interesting. And the one that is in the same place as the one that's getting hot, but on the opposite channel. Minus 65.9. Next one, middle pin, minus 65.4. And the last one. Minus 65.4. I just want to check something on the first one again. So we had effectively this one on the emitter minus 65.2 and this one plus 65.2. Okay, so we have some measurements. Let's see if we can make any sense out of it. While we're in this area, let's just measure the voltages on these little capacitors as well. So this one has plus 64, 65.6, 64.1. There's no do that. And what's on the other one? 65. 65.7. Let's have a look at these voltages then. I haven't looked at how these actually connect to each other yet, but this is the side where it isn't getting hot. So we have BF393, this is an NPN transistor, MPSA92. This is a PNP transistor. Let's figure out if they should be switched on or switched off and how they're working. So on this transistor we have all negative voltages, and we have between the emitter and base is NPN, so the base should be higher than the emitter by about 0.6 volts to switch it on. So the emitter is minus 65.9 and the base is minus 65.4. So the voltage here is actually about 0.5 of a volt higher than the emitter. So between the emitter and the base we have about plus 0.5 volts. Yeah, that's possibly enough to just about turn it on. Okay, make it read a bit better. I'll put it here. So the bias, we'll call it on this one, is plus 0.5 volts. That's the base emitter voltage. Okay, this one, although the voltage looks strange, we actually have again minus 14.1 on the emitter, and the voltage here is a little bit higher, minus 13.7890. So this one, the bias on the base is a plus 0.4 volts, which you'd think would be switched off probably. Okay, so that's that. Now let's see if they are on or off. So this one, the collector is a very similar voltage to the emitter. So that suggests this transistor is actually on, or just about on. This one, the collector and the emitter are completely different voltages. So this would suggest this one is off. Okay? Let's look at the other two. These are PNP transistors. So here, the base has to be negative with respect to the emitter to turn on. Well, this one clearly has 65.8 on both. So the bias on this one is 0 volts. Yeah? And we can see the emitter and base are completely different. Minus 65, plus 65. This transistor is off, and it should be off. Yeah, no bias. What's on the other PNP? Well, we've got 65.5 and 65.6. Sorry, 65.5 and 64.9. These voltages are on the capacitors, by the way. We'll come to them in a minute. So here, 65.5, 64.9. So again, in this case, the base is a higher is a lower voltage. That's plus 65, plus 64. So again, this transistor should be turned on. The bias, the base is about 0.6 of a volt less than the emitter. Minus 0.6 is the bias. And the transistor looks like it's on, plus 65 on both ends, on. So that's what we have. We have, on this channel, we have the NPN, the BF393 is on, and the PNP is off. And I'm assuming that's the good channel. It's not getting hot or warm on that transistor. This one is the opposite way round. So here we have this one is off, just maybe conducting a little bit, which is why it's getting hot. It's kind of on the threshold of coming on. To get hot, it must be passing current. So we'd have to assume that bias is just enough to turn it on. Maybe I was 0.1 volts out on the reading, yeah. And this one is on compared to off, yeah. So we see we have a different condition on both channels. That's what we were looking for. The capacitor, this one has 65 on one end and 65.7 on the other end, so about 0.7 of a volt across it. And this one's 64.1 and 65.6, so this has a higher voltage across the capacitor, about 1.5, sorry. That has about plus 1.5 volts across it, and this one has about plus 0.7 volts across it. Well, here's the interesting thing. So the ones I'm particularly interested in are these two voltages, because they're so different from all the other voltages. This is the transistor that had previously gone, but it hasn't gone now. So let's see if we can figure out where the base of these transistors, and for that matter the emitters, actually go to on the both channels, and see if we can then figure out why this one seems to be wrong. And just to mention, the fact this is off on, this is on off, they're in opposite logic states, yeah, they swapped over, which is why I think this is creating a protect error. Obviously this transistor is getting warm, which means it's passing current, so I'm assuming the bias here is just enough to turn it on partially. I mean, maybe if it's not quite accurate on the measurement, it might be, you know, 0.05 of a volt more. I could measure again, but that's the readings I got. But with a transistor, and if you watch my video on transistors, basically when the transistor is off, it dissipates no wattage, because with the transistor off, there's no current flowing from the collector emitter, therefore there's no wattage. When the transistor is fully on, yeah, like so this has like a, well, I've drawn an NPN, so this has 0.6 of a volt on the base. This is now on compared with the emitter, yeah. What happens now is the transistor switches on and the voltage across the transistor is very low. So watts, which equals volts times current, although the current can be high, the voltage across the transistor is practically zero, and practically zero times something is still practically zero, so it doesn't get hot. When you have a situation like this one, this transistor has got a very large voltage difference across it, yeah, but of what is it, very large, 77 volts or something across it, but it looks like it's been biased enough to turn on a little bit. So here you have some current flowing down here controlled by the bias and a large voltage, yeah. And in the case here, watts equals voltage times current. When voltage is high, 75, and current is something, yeah, it's some current, then the wattage is something times 75, which means it's going to get warm. So that's another reason why I think this transistor is actually biased enough to switch on. And I'm still of the same mind as to figure out where these voltages are coming from, because there's something clearly wrong here. I just need to interrupt my own video here to clarify a couple of things actually. The first one is that I did measure the voltage on the emitter wrong, and it's 14.41. So this transistor is quite clearly on, and the base bias is plus 0.7 of a volt. Now, when a transistor is switched on, you would expect the collector and emitter to have basically the same voltage. But in this case, the circuitry either side of it, so there's a resistor here and there's another resistor up here, is effectively preventing the transistor from having a low voltage across it. So the transistor is passing some current limited by these resistors, and it has a high voltage across it, so it's getting hot. That's why the transistor is getting hot. This transistor, due to the components around it, is acting in a configuration known as an emitter follower. It's most easily pictured like this sort of circuit, where you have a resistor going to the base of a transistor and then another resistor effectively to ground or some voltage. Or this resistor quite often can be a Zener diode. Yeah. And the point of this circuit is that the resistors around the base set the voltage on the base. And here we have a resistance, which is either a resistor in series with the transistor, or that resistance is effectively the load connecting to ground. Yeah. And this is your voltage in, and this is your out, and this is what's called an emitter follower. So basically, if you put on here, say 12 volts, the emitter will rise up to effectively the voltage drop across the junction, and we know a diode junction is about 0.6 of a volt. So the emitter voltage follows the base voltage upwards until it reaches about 0.6 of a volt across base emitter, and the voltage on here is about 11.4. That's how an emitter follower would work. Now, if you were feeding in here, for example, 15 volts, you can see the voltage across the transistor is what, 3.6 volts? Yeah, 3.6 volts across the transistor emitter collector. So this will regulate the voltage coming out, but because of the voltage drop across it, yeah, not like 0.2 of a volt, the wattage will be that voltage multiplied by the current flowing through it, and the current flowing through it will depend on the value of this resistor. So effectively that's what this circuit is doing. It's not supposed to do this, it's just that because there's a fixed voltage on here, it's working that way. Okay, that's one thing I wanted to clarify, and I hope I did. And if you still don't follow it, I can talk about these on another video, but I have done transistors, so I'll link the all you need to know about transistors and the other transistor videos I made, and if you want to brush up on transistor theory, that will explain this very well. Okay, that's one thing. The other thing I want to clarify, because I know this is confusing a lot of you guys, I'm sure, is all these negative voltages. When you're thinking, well, an NPN has positive voltages, why is it working with negative voltages? Well, the reason for that is because you need to understand one very important thing. There's no such thing as a negative voltage, or for that matter, as a positive voltage. All there is a potential difference between 2 points. I'm measuring on my circuit from ground. Yeah, so my black meter probe is on ground. This is my meter, and it's an analog one because my pictures are always analog ones. I'm measuring from ground. So the other meter lead, I have two voltage supplies. I have plus 65 roughly and minus 65 roughly. So when I probe in this area of the circuit, I will read a negative voltage, and when I'm probing in this area of the circuit, I will read a positive voltage. But really, the positive and negative doesn't resist. If I connect the ground of my meter probe to here and not to there, everywhere I probe in this circuit now will be positive. And the highest positive voltage I could read is, if I read here, is 130 volts, because 130 volts higher than here. And if I measure ground, ground will read plus 65 volts. So this is very important to understand. You read the difference between 2 points. Negative is it's a man-made principle, I guess. There's a word for it, I'm sure. But it doesn't really exist. So let's look at this circuit again now. And now let's put our meter probe here. The black probe, yeah? On our meter. Now let's take the red probe and let's measure here. Okay? If this point is now effectively, we're using this as our reference, we're using this as ground. This point is a little bit higher in voltage. It's less negative here. And it's a little bit higher by 0.7 of a volt. So on our meter here, with the black lid on here, we would read plus 0.7 volts. And if we put our red probe to here, the same place as the ground, we would read 0 volts. Yeah? This paper's getting messy, isn't it? And if we were to measure here, we would read the 14.4 plus the 63. Yeah, so you would actually read that's 64 plus 14. You would actually read 78 volts plus on the collector. Now does it make some sense? 0 on the emitter, plus 78 on the collector, and plus 0.7 on the base. Therefore, the transistor is forward biased. It's turned on like this transistor. But we've now got from the collector to the emitter 78 volts. Yeah, can you see it? We've got a high voltage across the transistor. The only reason it hasn't burnt up or blown up is because the resistor is high value here and here, and the high value resistors are preventing a high current flowing. But a small amount times 78 is still going to be quite a bit of wattage, so it may be dissipating half a watt or something. You would have to measure the resistance, then you know the current. So if we measure across one of these resistors, the voltage drop, we know the value of the resistor, we can work out the current through the circuit, and we work out the wattage. But we know from the fact the transistor is getting pretty damn warm, and the transistor can dissipate 0.625 of a watt. It's probably dissipating like half a watt or something like that, maybe. Anyway, I hope that has clarified that, guys. So I needed to put that in, really. And yeah, let me know in the comments below if that's any less or more clearer than mud than it was before. Okay, guys, I think I might be getting somewhere a little bit now. This is the transistor that has been effectively turned on when it shouldn't be. This is the one that gets quite hot. Whereas if you look at the equivalent transistor on the other channel, it doesn't get hot, it's switched off. Now, what switches this on will depend on the base emitter voltage, effectively what is on the base. And the transistor, we can see the emitter, which goes to here, goes through a resistor, this one, which is 4.7k, to this track, and this has a negative voltage supply on, quite a high negative supply, like 63 volts like we've seen elsewhere. So that's that track, and I'll show you in a minute what's on it, the other side of the resistor. Now the base comes across here to this resistor, so this is the base, and this goes through a resistor which is another 4.7k, and this here is a transistor, but it's wired quite unusually, so the base and collector are shorted together. The emitter of this one goes to a resistor here. This one's a higher value, about 60k, and it comes to effectively this track, which has 3 resistors attached to it. So we can look what's on this track, we can look at this base emitter, but it appears to me that whatever voltage is on this track via this resistor will set the base voltage via the other resistor of this transistor. So that will be set by whatever's on here, and this I suspect will be a lot to do with what's on the emitter. It's the emitter base difference that switches it on or off. So that's that one. Now, if you look on the other side, we have the same arrangement, but the transistor with the 2 pins connected together is here, physically the opposite way round. So this is the one that's switched off. Again, the emitter goes to a resistor here, and this goes over to here. through a 4.7k. I think this one has a high negative voltage on it. The other one has a high positive, I think, on the collector. Yes. So that goes to there, and then we have the same circuit. So from the base of this transistor, if I just trace it for you, here, it goes to another resistor here. Yeah, that's 129k. It also goes to this resistor, which comes back to here, 4.7k again. And this is the transistor. Sorry, just off the screen. This is the transistor that has the base emitter connected together again. And again, the emitter of this goes to a resistor here. And this on the other side is a 55k resistor. But on this side it reads about 20k. I can see a difference on the value of this resistor here. So let me just check the voltages now. Let me just see if that resistor's a problem on the other side. I think it will come a little bit clearer if I do show you the voltages on this part of the circuit. Or it might just be as clear as mud. Yeah, I mean this is quite an involved one, this, and sometimes you get them, and the only way to fix them is to keep at it basically until you figure out what actually is wrong. This is the good channel. You can probably see like the 3 tracks connected together there, the same as on this one, yeah, this track. So look on here, on the bad channel we have minus 7.6, and on the good channel we have minus 7.5, so that's almost the same. I'll just make a note of that on my drawing, minus 7.5, 7.6. Now if we look on the base emitter that are connecting together, which connect from that point, so the resistor comes through here, and this is the emitter of that transistor. So this has minus 65.8. Make a note of that. And on the bad channel we'll just find the same point. So this is our transistor with the base collector connected together, and this has minus 5.4 on it. Yeah, minus 5.4. So there's a big difference in the voltage there between the two. Once again, just double check. The one with this one here, minus 5.4, on the other side minus 65.9. So there's a big difference there. We then go to the collector. Let me just find it. This then goes to this resistor. So there's the minus, the base collector on this minus 13.2. On the other one, base collector connected together, minus 65.5. So I'll make a note of that, minus 13.2, minus 65.5. So I think that's all I need to measure. Now let me show you on the diagram what we actually have. So this is basically the circuit we have. This is this transistor wired with the base and collector joined together, which to me I think is acting kind of like a diode, but I've read somewhere it's some sort of constant voltage or current thing. It's an unusual configuration. But what we basically have on the bad channel and on the good channel, so both channels, the voltage at this point, this is the track where the 3 resistors all join together, minus 7.6, minus 7.5. The purple ones are effectively the good channel. On the emitter here we have minus 65.8, but on the bad one we have minus 5.4. So there's a big difference in the voltage here, and this is the resistor that reads completely different on the 2 channels, and I think it might be open circuit on the bad one. This resistor then, the one connected to the emitter of this rather oddly configured transistor, and goes to the track where the 3 resistors all connect to each other. We can see this is the track with the 3 resistors, and this is our transistor with the 2 base collector attached to each other via a circuit track. It's supposed to be like that. The emitter comes to here, and this resistor to this track reads about 55 kilo ohms. Okay. On the good channel, supposedly, the transistor which is configured with the emitter sorry, base collector attached together is this one. Okay, this is the emitter, goes to this resistor, and again the other end goes to this track with the three things attached together. And this one is reading, what's that like? Oh, that's strange, it was reading different one way to the other, but that's reading 15, 16 kilo ohms, and it's climbing up like we have a capacitor charging somewhere. Okay, and it eventually stops at about 20 kilo ohms or thereabouts. Okay, I'll just measure the other way. Yeah, it's a capacitor charging somewhere, it's now charging the opposite direction. But we can see it's reading about 20k, as opposed to, and I'll make sure I'm in the same direction, it's this one, 56k, and it doesn't climb up. So I think that's where the problem might be, or a problem. It seems as like it may have several problems. Let's check these resistors and see what value they are. This is the transistor that gets hot. This is the one that was faulty that I replaced, and it tests okay in circuit now after I replaced it. It didn't test okay in circuit before. So for this transistor that gets hot, this is the one with the base collector attached together, and this is the emitter. It's marked E on the board, and this goes to one of these resistors. I'll just find it. This one, okay, and the other end of this resistor, it reads 55k. So that's the resistor, and if you just get a torch and have a look, it seems to have a band with a red in it to start off with, yeah, which is a 2. So I think that's reading wrong. It's reading higher than it should do. On the good channel, that's here, the transistor is actually the opposite way round. So this is the one that has the collector base attached together. This is the emitter, and again this goes to a resistor in here. I'll just find it. That one, okay, and this one reads across the resistor, we saw from the other side of the board, about 20k, climbing up with the capacitor. And if you look, the markings look to be the same. So let's remove the two transistors, the two resistors, and see if anything there is faulty. It's actually easier from this side of the board to see which ones they are. So while the desoldering tool is just warming up, let's add a little bit of leaded solder to this. So I think you can see even more clearly now, this is the one that has the base collector connected together. So we've got a bit of solder in here. There's solder on here. This is leaded solder, just helps really with the desoldering. This is the resistor. Sorry, this is the resistor. I got the wrong one. This is the resistor. And it goes to this stretch on here, yeah, with the 3. So we need to desolder those. And then on the bad channel, where we got the stranger voltages, this is the one with the base collector attached together. So that's this one. This one. This is the emitter. This is the resistor. And again it goes to this end of the track here. So let's get these things out and then let's see if this helps us to solve the mystery. I'll just clean my desoldering tool, always worth doing before you just use it. These things are a godsend, by the way. If you're serious about repair, you should buy one of these. This will save you so much hassle. You see that's slightly clogged up, doesn't want to go past there, so we can soon deal with that. There we go. Okay. Right. It's best not to use flux when you're using one of these, by the way. The flux clogged them up quite badly. So here's our transistor. Let's get this out. Okay. And then the resistor. You see why these things are so good? Okay, and then on the other side, so we have the the transistor. Okay, and the resistor. Our transistor is nicely desoldered and should just come out of the board without too much hassle. Yep, there we go, one transistor. You couldn't see it because you let me get where you can see it. So that was nicely desoldered. There's the transistor from the good channel. And the resistor again looks like, I'll just make sure the legs are free. Yeah, you can see it wobbling. So again, that's nicely desoldered. And this should come out the board nice and easy. So let's get it. Okay, there we go. Now let's get that out. Here's the resistor then. So the resistor, it's probably too much light. Looks like some red straps. I'll probably have to use the magnifier. The transistor is a BF393. Let me see what value this resistor is. One moment, I'll use my magnifier. Well, although it's reading 20 something ohms, it looks like it might be a 56k resistor. Green, blue, black, red. Let's check it with the meter and see what it says it is. The meter. I mean, considering the other one was reading 56k, but this was reading 22 and the capacitor charging. So the resistor is in fact a 56k resistor, which makes you think the other one is now okay. And we'll use the transistor tester on this and see what this looks like. The transistor should be an NPN transistor. Let's see what we've got. Yeah, NPN silicon transistor. And that looks good. But this is the effectively good side. Let's have a look at the bad side and see what we get there. These are the ones off the bad side, and I think this is going to read 56. Just check on the meter, see what we have. 56. That doesn't surprise me because the other one was a 56. So we'll put that out of the way and we'll test this transistor. But I suspect this is probably going to be good as well. And then while they're out of circuit, let's have a look to see what we've got now. I think we've got an open circuit somewhere, which is why the other one was leading a lower resistor, and I can see a capacitor charging. And I might be able to spot it with these things out of the board. One moment, just get the clip onto the transistor. Okay, we're on. Oh, we were on. Let's go again. Okay, we're on. Let's try it. Yeah, so again, it's a good transistor. Right. So they are good. So while I've got the ports out of the board, let's read across this resistor again. Let's see what we can see. You can see clearly now where I've taken the ports from. So this is the one that read 20 something. You see, that reads about 27, 28k, yeah? I'm reading something. This one reads open. So I've definitely somewhere reading something on this that I'm not reading on this. The thing is, I can only see that this goes to here. And I can only see it goes to here. And I know this has got the same voltage on both. There's probably some track on the other side of the board, and I need to have a quick look to see where it's going and not going on the other one, yeah, if you see what I mean. Yeah. There's two other things attached to here. Let's just see what resistance we see on these. So that's from here to here. And that's really 7.46k. And then the other one looks like it goes to here. Oh no, this is the end of a transistor. No, the transistor's there. It's not the end of a transistor. It's probably a resistor. That reads 6.7k. Let's have a look on the other side. So from this point to here, yeah, 7.4, and from here to here, 7.9. So that reads the same on both. The problem appears to be wherever this is going. Let's check the resistance from here to ground. Well, that's open circuit. What about the other one? Oh! Well, we see a capacitor charging, but there's something there. Let's go from here to positive power or negative. That's one of the power rails. How about the other one? Well, we read quite resist high to both. How about this one? Again, we're reading differently. Oh, right. So this one here goes to one of the supply rails coming in. Let me see which one. This is the end of the resistor that goes to the emitter of the transistor. And this connects to here. Yeah. And the other one on the other side doesn't connect to there. And it doesn't connect to here either. Whereas this one, we kind of like see a capacitor charging. So I'm guessing that should connect down there somewhere. I need to look on the other side of the board to see where these tracks go to, because there's nothing on this side. Well, this is all a bit speculative, but this is what I can see. This is the side that doesn't get hot, and this is where I've removed the transistor, and the emitter goes to here. This is the I think it's the negative supply rail. Well, I can just check actually. Is it positive or negative? Yeah, it's the negative supply rail. Goes to here. Okay, so that emitter goes to the negative supply rail. Okay, on the good side. Now I thought to myself, well, if that goes there and this circuit is monitoring the negative supply rail, it should be monitoring the positive supply rail somewhere as well. So what I decided to do is go onto the positive side and then go across all the emitters and see if I can find any of them that attach to positive. Okay, and I'm just going to cross all the emitters now. And that one, which effectively is the one that's getting hot on the other side of the circuit, goes to the positive supply rail. Okay, this one doesn't go anywhere. Now we're on the other side, so coming into the same position, it's this transistor. This is the one that gets hot, and it goes to the positive supply rail. So both that one and this one, symmetrical, connect to the positive supply rail. Yeah? So then you think symmetrical, given the fact that these two are kind of opposite way round, or the one that's connected to base, should go to this negative. Or there's another emitter on here connecting to the negative supply rail, because you'd assume one of them must be, because this side has one emitter connecting to negative. Yeah, so one of these on this side you think must go to negative. So I go across all of these. Yeah, and none of them connect to the negative. None of them are sensing the negative, and I'm pretty sure this one should be, because the same one on the other side basically does. Albeit this is not quite symmetrical, but we know about that. So it's looking like this should go to there, and doesn't. The question is then, how does it go there? Because I'll show you on this board, I don't even see how this one gets there. This is the one that goes to the negative supply rail. I mean, I can triple check, but I'm going to sure it's this one. So I'll go on to the emitter, and you can't see me do it by just going to the transistors. And it goes there. Well, if we look on this side of the board, there are no tracks. Yeah, there's no connection from there that I can see, unless you would think it's on the other side of the board. Okay, but it's not. This is the other one. And again, there's no tracks going from this side of the board on the emitter. Turn it over. Well, yes, there's a track which goes to here, but it doesn't go anywhere else. And we know that's a 56k resistor, so it can't be connecting through there. And besides, I've removed them on both channels, yeah, neither of them are there. And yet, this one still somehow is connecting to the negative supply rail. See how yeah, there. It's somehow connecting to the negative supply rail. How? Because I can't see it. And then you sort of wonder, well, is that the faulty side? Look, I'm shining underneath. I can't even see any. Ah, now I can see. I couldn't see any connection, but now shining from the other side of the board, I can see the connection. It comes from this pad and goes off in that direction. Ah, I solved that mystery. Let me see if I can see where that's going to. But it's looking like I might just have an open circuit trace, basically. Well, it goes down under there, and there's obviously from the other end of the resistor there's a trace. But to see where they go, I have two options here now. One is to connect a piece of wire from here to the negative supply rail. Yeah, just connect a piece of wire. And the other one is to take the transistors and heat sinks off the board and have a look to see if that's where it should go. But all the evidence is pointing that that is where it should go. Well, I think I can see it actually, and this is by shining the light from underneath and looking through the board. So I think you can see that from the emitter, from the end of the resistor where I've actually removed the resistor, that's this point, yeah, from there, right? You can see a track, and it goes sideways underneath all these other resistors, and it ends up at the other place where I've removed the resistor. But look in the middle, you see under there, under this resistor. Let me put the thing onto the other wires where I can. Yeah, there you go. So I'm sure you can see it, because I can clearly see it. This track, which goes under here, appears to have a break in it there, and then goes to there. So we're going to have to take this resistor out and have a look to see what's going on underneath it. Look at that. That seems to be loose. With these things, you always should clean them before and after use. It just makes life easy. It won't clog up on you if you do that before you put it on one side. Right, let's get this resistor off the board. I can check the resistor, but this is off the, effectively the good side. So I'm pretty sure it will be okay, but let's have a look. It may as well be nothing but thorough. Yeah, this is our resistor. Let's get the meter where you can see it. Reveal the meter, yeah. Bit of revelation going on. Reads 10k. I mean, that's such a sensible value, I'm sure it's correct. So that's the resistor. Now what's going on underneath here? Can I see anything? Let's get the torch around. Yeah, I can clearly see something's there now. A piece of track's blown away. Can you see it? It's like, you can probably even see where it's like kind of vaporized. So something has caused that track effectively to go open circuit just there. I don't know if this is maybe the faulty transistor that I've already changed, but what we need to do is put this back together, and probably from the other side of the board, I think is going to be easiest, solder a wire across these two resistors. Yeah, let's do that. Just before I do that, I've actually cleaned this up with a bit of ISO, and now you can clearly see where there's a piece of track missing. I'm just finishing putting this back together, and I've noticed that the centre via out of this hole has actually come out of the board. It was stuck to the transistor. Now that, if you solder it in, would probably mean that if there was a connection from this side of the board going somewhere here, that you probably wouldn't make a connection. You'd probably have to fix that first by soldering a wire from wherever and dropping it through the hole before you put the transistor in. But in this case, if we just shine through, you can see that there isn't any track on this side of the board. So it's not necessary to repair that damage, but otherwise it would do. So if when you're looking at the transistor, you see like a little round thing and it comes off the leg, that's what it is. It's the via out of the hole on the board. And you need to have a look to see if you need to fix that problem before you go any further. I just about have this back together now. So this is the end of the transistor with the collector base connected together. And this is the resistor it goes to here. Okay. Here. And then this goes to this little rail with the 7.5 volts on. And this end of the resistor effectively is the one that goes to the negative supply. Yeah, just like a negative supply rail coming in there. So that goes, in fact, I think you can probably see it over here. No, you still can't see where I am. But that's the one that goes to the negative supply rail. So we need to connect from there to this end of this resistor over here, the one that's reading effectively 56k to here, yeah? We can either bridge from the two emitters or the two ends of the resistors. I might actually do it at this side of the box. I think there's a little bit more space than there is here. So I'm going to take a piece of wire and bridge these 2 points together. In the end, I soldered it to the two emitters. It just seemed easiest. So let's just check now. So from the emitter to this place here is now actually reading, you can see resistance climbing up, yeah. Then we go on the other side from here to here, and we now have a resistance climbing up, so they're now the same. So let's put this back together. Let's put our light bulb in circuit and let's see if nothing horrible happens, and if so, let's power it up and see whether we now have the protect light going out. It's back together, so let's try it. So what we're looking for is this protect light going out. I've connected it via the light bulb, which you can see under here, which will stop anything very bad happening if we've created some major problem here. So let's switch it on and see what it does. Well, it's powered up and going dim, so that's a good sign. So we can, yeah, we can switch off and we can just power it up. And the protect light went out, it clicked, you heard the relays. One thing left to do then, and that's just to try it, yeah. It's back together for the main part now. Just need to put all the panels on, but let's see if this is actually working now. Let's just cue something a bit funky, yeah. Let's see what we can find. Okay. Yeah, that's oh, definitely that's working. Okay, so yeah, I think this one can go back to the guy who owned it now, and he'll be happy. Can't beat the old ones, eh? Okay, there you go, guys. One mixer fixed. So there we have it. Did you watch it, guys? I hope so, and I hope that if you did watch it, in fact I'm sure if you did watch it, then one of two things will have happened. Either one, you have definitely learnt something on this journey and hopefully pushed your own boundaries, and now your own abilities are higher than they were before. Or you were some steps up above me, because I ain't the best tech out there, that's for sure. And you are probably shouting at me at various points in this video, telling me why I should be doing something different that would have found the problem much quicker. But hey, you know, that's life, that's it. I'm learning the same as the rest of you are learning. So I'm very, very interested to see your comments below. whichever of those camps you fell in, or if you just thought the damn thing was just far too long. Yeah. For those of you who skipped through it, yeah, I hope you enjoyed it, guys, but I think you will have missed a number of things that you really should have learned here. Okay, that's enough for that one. I'm going to do something a little bit less stressful in the next video, I hope. But I never know until I plug the damn thing in, yeah? So I'll see you all soon on the next one. Ciao for now, guys.